Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I've been guiding you through the chemistry course. In this lesson, we'll be looking at atomic structure 2 and the periodic table 2. We'll consider the atomic structure, we'll consider the atomic emission spectra. We'll also look at the atomic table and periodic table rather, and atomic properties. Alright, let's get going. So, our prior to now, we've looked at the discovery of some of these substances. So let's go over it again. Let's look at how we made the discovery of the structure. It has been assumed that inside the atom is the smallest indivisible particle of an element according to Dalton, but it was discovered by Mr. J.J. Thomson in 1897 that the atom actually contains more than just one thing. He bombarded the atom inside the cathode discharge tube, and he did the experiment first with 500 volts and then with 5,000 volts and then with 15,000 volts. And at 15,000 volts, he observed a green radiation coming out of the element. So irrespective of the element, a green radiation was coming out, and he noted it. The green radiation was subject to a magnetic field and it deflected easily. So he decided and said that the green radiation must have been an electron because it was attracted towards a positive magnetic field. And he went ahead to conduct further experiments to discover the amount of charge, that is the charge to mass ratio of the substance, and he calculated it to have been 1.76 times 10 raised times per 11 charges per kilogram. And then in 1910, R. Millikan did an experiment, and he found a way to discover the amount of charge that and the quantity of a charge, and he discovered it to be about minus 1.6 times 10 raised per minus 19 coulombs. So we could actually calculate what the mass of an electron is by dividing the amount of a charge by the specific charge, because that will give us the inverse of mass. So the inverse of the inverse of mass, that's mass, of course. That gives us 9.1 times 10 raised per minus 31 kilograms. That is the mass of an electron. And of course, let's talk about the discovery of the proton. The proton was also discovered by J.J. Thomson in 1898. In 1898, after he did his first experiment, he decided, okay, how about doing another experiment using a discharge tube also, but this time around moving the cathode point to the middle point of the discharge tube. And when he did this, he observed that while a green ray was going in the right direction, a red ray was going in the opposite direction. A red ray was going in the opposite direction. This red ray also is, when subjected to a magnetic field, negative magnetic field, it is deflected. It is deflected by a positive magnetic field away from the magnet. So he observed also that the level of deflection was not so much, which suggests that the particle this time around must have possessed a weight higher than the particle that he observed the first time. And that particle was named the proton, which is a positive electron. He went ahead to calculate the specific charge of this property, and he discovered it to have been 9.58 times 10 raised to the power 7 coulombs per kilogram. And this is approximately about 1,840 times as heavy as the electron. So we do represent our proton with 1, and we represent our electron with 1 divided by 1840. Alright, In 1900, that was what led to J.J. Thomson coming up with the concept that an atom is just there with pluses and minuses, up and down. He had this ideology that this is the way an atom looks like, all randomly arranged. So until 1911, we always believed that an atom looked like this. When Rutherford came up with the concept of the atom, but before he did, he encouraged Giger and Marsden to conduct their own experiment, which he watched and was marveled, and he went ahead to do further experiments, and he discovered that in the core of the electron of the atom is quite heavier than the outer part. In fact, the core is super small compared to the size of the entire atom. So that was when he came up with the concept that there is a nucleus and there are orbitals around the nucleus. And now on the orbitals we find there are electrons, and at the nucleus, in the nucleus, we'll find the proton and the neutron. So that was why we came up with the Rutherford's atom. Let's look at atomic number. Atomic number was created in 1914. In 1885, Röntgen came up with the concept of naming. He came up with a concept of looking at observing the wavelengths of different materials, how they react, the different wavelengths they give off after X-rays have been passed through them, and he started numbering these particular X-rays. In 1914, Moseley came up with the idea of, instead of naming the X-rays, why don't we name substances based on these particular X-ray numbers? And he started the concept of naming substances based on their X-ray numbers, and that name was assigned and was called the atomic number. But later we discovered now that our atomic number is not just a name of the substance based on the radiations of the X-rays. Rather, it is the name. It is based on the number of protons contained in the nucleus of the substance. In 1932, Chadwick conducted his own experiment, bombarding a tin gold film with an alpha particle, and he observed something new. A new substance was liberated, and it was a neutron. And that was how it came about the discovery of the neutron, which actually he discovered was not deflected by any form of magnetic field, and it possessed a very, very close, in fact, a mass of almost exactly the same size as that of the proton, a little heavier though, but about the same mass. So he discovered that the difference wasn't much. We just took it, and we have understood always from the time of the discovery of the protons, we had understood that the mass at the nucleus was always like twice the mass of the proton. That is what was pushed out of the entire setup at that particular point in time. So that simply helped us to understand further what was really happening in the system. When we consider the nature of light, of course, all these things we've been talking about, emissions and all, we discover that it is light that is being emitted. When we take note of the nature of light, we'll discover that light exists both as a wave and as a particle. As a wave and as a particle. Well, while describing light as a wave, we come up with the formula C equals to V multiplied by lambda, where C is the speed of light, V is the frequency of emission, and lambda is the wavelength of emission. Of course, we know that it is waves that are propagated that have wavelengths. So we know that from this, judging by this, we can always classify light as a wave. But also we discovered that even in light, we have some particles known as photons. They are called photons, and they carry electric power, they carry charge, and they do possess a certain amount of mass. When we want to calculate the amount of energy that they possess, we simply multiply the Planck constant by the frequency. So V here is still frequency, and H here is what we know as the Planck constant. Is the Planck constant. Alright, we've said so much in so little a time. Let's take a short break, and when we come back, we'll continue in the lesson. But while we are on this break, some questions will be displayed on your screen. Please do well by answering them. We want to see what you've understood from what has been taught in this lesson so far. Welcome back. So, we talked about the atomic structure. Let's start looking at the atomic emission spectra. Then we'll go into other things still inside the atomic structure. When we talk about emissions, earlier in these lessons, in our earlier lessons, we talked about emissions coming from metals when certain radiations are being exposed, when they're being exposed to certain radiations. And we said that different kinds of emissions are being given off. We talked about sodium, that it gives us a yellow, bright yellow kind of light. Well, we observed that when this particular sodium light is being viewed in a kind of a spectrum, instead of it coming out just the way it appears when we are passing light through a glass prism, it appears in a different way. You see the lines, a unique line to show each particular spectrum. That is to explain to us that it is not like a range. Rather, there is specific value at a specific amount of energy. A specific electron will achieve a particular orbital or spectrum. So, just like we discussed then, we are emphasizing it again. The same thing happens when you take hydrogen and you take observation, you take note of the spectrum of hydrogen, and we are observing the energy levels within hydrogen, being the univalent, being the element with only one electron on one particular charge. They were able to observe it closely, and it was observed that the wavelength can be calculated using the expression 1 over wavelength equals to R multiplied by 1 over n squared, n1 squared minus n2 squared. Now, where this R is the Rayberg's constant, the n1 and n2 are simply levels in the orbitals. That is, either it is level 1 or level 2. Now, and the first one is always the higher level, while the second one is the lower level. So we can use that to calculate the wavelength. Now, looking at all these things, Bohr came up with a model for atoms. He says that after conducting his own experiment, he said Rutherford must have been correct, and atoms must have been moving about orbits. Of course, Rutherford was one that proposed that there are orbits in which atoms move, and he also suggested that the amount of energy it would take to set an atom, an electron rather, free from its orbit to another orbit, that is to get it excited or to bring it down from excitement, would be calculated by the energy it needs to be at that point of excitement, or would be the energy needed to stay at the point of excitement subtracted. We then deduct the energy at the new state, which is either the ground state or a lower level of excitement. And this led to us to looking at certain other principles. Then we came out to look at the concept of the structure of the atom. The concept of the structure of the atom. If we are talking about several stages, several levels, are we saying that within an atom that has this nucleus, this first shell, this second shell, and this third shell, is it that it will drop one electron to inside here and to attain that certain level? That was where one of the confusion, that was where one of the problems came up from. And then we came up with the different understanding of the different quantums, and that was what led us to talking about the quantum numbers. we have 4 different quantum numbers that we'll be considering. The first one is known as the principal quantum number. The principal quantum number simply tells us the number of the shell. It tells us the number of the shell, and the number of the shell increases from the core outward. Also, it is good to note that the maximum number of electrons that can exist in a particular shell can be calculated by the expression 2 multiplied by n squared. 2 multiplied by n squared, which suggests that the very first shell can only accommodate 2 electrons, because when you put 1 there, 1 squared will give you 2, will give you 1, 1 times 2 will give you 2. So that is why after hydrogen and helium, no other electron, no other element can be found on the first period. And then we'll move to the next period, which is the second shell, and we'll say, okay, that will be 2. 2 squared is 4. 4 multiplied by 2 gives 18. So we're saying 4 multiplied by 2 rather gives 8. So we're saying 8 electrons can be found on the next shell, which is this particular shell. And we labeled our shells, of course, we labeled them K, L, M, N, O, P, Q, R, like that. But for now, let's just work with K, L, and M. So in our K, we can have a maximum of 2 shells. In our L, we can have a maximum of 8 shells. M, 18 shells, because 3 squared is 9, and 9 times 2 is 18. That also makes us to think about the next level of a quantum operation, and that's where we consider the azimuthal quantum number. When we're talking about the azimuthal quantum number, it is a quantum number of the angle of the axis about which the element, that's the electron, the angle about the axis at which the electron is spinning, the angle at which it is moving. So when we consider that, also we have to also split down, and we describe the azimuthal quantum number as L, as we represent it with the alphabet L, small l, and small l can be calculated by n minus 1. N minus 1. When we look at it, the first shell only has 2 electrons, so it does not have any azimuths. The electrons move in just one singular plane. But the second one has 8 electrons. So when we subtract second, that's 2. That means it has 1 azimuth. 1 azimuth. So that azimuth now will go about the axis about which the electrons can rotate. Then we'll go to talk about the magnetic quantum number. The magnetic quantum number is always rated between -1 to 1, and that of course will exist. It depends on the azimuth. It moves -L to L, -L to L. So if our azimuth is 1, it will have -1 to 1. If our azimuth is 2, it will have -2 to 2. And of course, -2, -1, 0, 1, and 2. Of course, if it is 1, -1, 0, 1, and like that. And then we'll consider the final one, which is the spin. The spin is always between -half and +half. It's either -half or +half. On your screen about now, you have a diagram showing different shells and the kind of azimuth and energy levels that they do display. Of course, we also have what we call the sub-levels. We have what we call the sub-levels. I forgot to mention while I was talking about the azimuthal. Of course, it's in the azimuthals that we find the S, the P, the D, F. These are the sub-levels at which these particular electrons do exist. They are the sub-levels at which the electrons do spin. So in a few seconds also, you see another chart that is showing you the number of orbitals in each sublevels. When you consider the number of orbitals, it tells you the M. That's why you talk about the magnetic value. So you see the number of orbitals in each sublevels, and of course that helps us to place the elements. Each element is just a spin. Each electron is in just one spin. An electron is in a singular spin. All right. So if we want to represent oxygen now in the electronic configuration for oxygen, that's we're using magnetic electronic configuration for oxygen. Oxygen, we know it is 8 electrons. That's what it has. And out of these 8, 2 will go to the first shell, 6 will go to the second shell. So the first 2 that go to the first shell, all of them will fill in. Of course, our first shell will be completely occupied, and it will be completely taken care of by the 1s group. Of course, we see the 1. The 1 is to tell us that it is in shell 1. And then the 2 is to tell us it is in shell 2. While the s is telling us that it is on the azimuthal plane of s, and the p is telling us it is in the azimuthal plane of p. And then our magnetic and spin covers the rest of the arrangement within the system. So now, after we have arranged these 2, the first 2, then we'll go to the next one. Of course, there is this particular drawing we're supposed to draw that will help us understand how we choose what is the next place to occupy. Where is the next place? So to pick our orbitals, how do we do it? We draw this particular pyramid. We can also have it completed all the same. That's 6F14, 7D10, 7F14. Of course, our F will always have 14 electrons. Our D will always have 10 electrons. Our P will always carry 6 electrons, and our S will always carry 2 electrons. So we'll cross out from bottom up downward, and that would tell us how the arrangement would be. Sorry. Down upward, rather, not up downward, down upward. So let me just stop at this point. So if we want to arrange it now, we'll have our 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we'll now have our 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Before we can have 4f14, 5d10, and like that on. So based on this, we'll just pick the amount that we need for this particular element. We're having oxygen that we're taking into consideration. Oxygen has a total of 8 electrons. So these are 1s2 orbital, that's 1s orbital, and of course the first and the second. Our 1s orbital is completely filled up. Then we can go to our 2s orbital. Our 2s orbital also on and down. That one is also completely filled up. So we have spent 1, 2, 3, 4 so far. We have 4 more electrons to go. Then we'll go to our 2p orbital. Of course, we have used this, that this is next. 2p orbital, you first fill up 1, 2, 3, we have one more, and that is how we fill our electrons into their individual spins. So we'll fill it one after the other, go in forward, then we'll come back to fill one more time. All right, when you look at the shape of the orbitals, you discover that the s orbital is spherical. Of course, it's spherical, while the p orbital is in dumbbell. The d and the f are having very complex structures, so we don't actually concentrate on it, we don't look at them. So the s is spherical, the p is a dumbbell, and the p of course have 3 different dumbbells because it depends on each of them. As each of these p's has 2p, each of these p's has a zone. This particular one is 2px, this is 2py, and this is 2pz. So each of the p's has its own specification. So this one is the x-axis, and this is the y, and this is the z. So those are the shapes of the different orbitals. All right, let's go into the periodic table and look at the periodic table in comparison to the atomic properties. When it comes to the matter of the relationship between the the periodic table and the properties of atoms, then we must agree that there is a lot of interesting things to look out for. Since the periodic table was actually designed because we wanted to establish the relationship between different elements and other elements, and then we try to arrange the table. That's the reason, that's the main idea behind the creation of the periodic table. Then it is believed that the periodic table should be able to solve almost all the problems. At least it should be able to give us a good description of what is happening to all of these elements. Let's take a look at what happens to these elements in the periodic table. We'll be considering the behavior of elements in the periodic table based on their atomic sizes and their ionic sizes. We'll also consider their ionization energy, their electron affinity, and electronegativity. And based on atomic sizes, we know that atoms, the element is getting bigger and bigger as we go either across the table or down the table. But the interesting thing to let you know is that across the table, instead of the element getting bigger, it's actually going to get smaller. Hydrogen atom is actually bigger than helium atom. The question is, why? Well, I can tell you why. The number of the amount of force, the force of attraction between if you remember, our atom is made up of a nucleus and the shell. Now, the amount of attraction between the nucleus and the shell will determine how far away the shell can go. When there is enough proton in the core, in the nucleus, when the nucleus has so much of proton and there is enough electrons, the protons will pull the electrons with more force, thereby reducing the amount of distance, or the distance between both the shell and the nucleus. That is the reason why helium has a smaller size compared to hydrogen. It has a smaller size compared to hydrogen, and this also happens to all the other elements as we move across the table. Let's draw a periodic table so that we can look at that as we walk. Of course, our periodic table is something like this. I like to place my hydrogen here. I'll just leave the space for the transition metals. I'll pretend as if they are not there. Let's pretend as if we can see them there. So we have helium here. that space won't be enough. That's well, let's just cover it all. 1, 2, 3, 4, 5, 6. Okay, I don't need that much. So this is good enough. Let's leave the space for the transition metals, since we have enough space for that. So this will be the space for the transition metals. And let's fill in our first 20 elements. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, we have chlorine, argon, then we have potassium and calcium. So after calcium we have scandium and the rest of them, titanium and all, tellurium, but we're not going to be focusing so much on those ones. We will just be looking at this first 20 elements, and we use the knowledge of that, generalize it to the others. So we have hydrogen here. When we talk about across the group, across the period, it means this direction, and when we say down the group, it means this direction. Now across the period, like I just explained, the atoms, the atomic size is reducing because of the pull of the electrons and the protons. But down the group, the size is increasing. The size of lithium is higher than that of hydrogen, and it is less than that of sodium. That of sodium is less than potassium, higher than lithium and hydrogen. Why? Of course, we know that sodium has the core, has the first shell that accommodates just 2 electrons, has the next shell that accommodates just 8 electrons, and has a third shell that has a singular electron. Now, you cannot compare this structure to lithium or even hydrogen that just has this. Because of the number of shells that have to exist, sodium has to be bigger. So this is our sodium and this is our hydrogen. Because of the number of shells that has to exist, sodium has to be bigger. So down the group, the atomic size increases, but across the size reduces. Now when we consider the ionic size is different from atomic size. When you talk about ionic size, across the group, it also reduces. Well, we remember what our ionic size is supposed to be. Our ionic size is supposed to be when it has lost or gained an electron. When it has lost or gained an electron, that is, it has become stable. Now, if you look at this guy, it will lose the electron to be stable. So it will actually be smallest. So it's supposed to increase, but it's smaller. It has lost an electron, but then there is no element in that shell. That electron is being tapped by another, so it tends to look biggest. While this one loses 2 electrons, so it tends to be attracted more, and it continues like that. While this guy wants to gain so much more electron, and because of the amount of force, it will be small. The amount of force will reduce it. It's actually having a smaller core before. Now it is having the opportunity of holding something. It will further reduce it, and the same thing will apply. And here it will be least, and this guy will be the smallest because it is actually balanced. The attraction between its own molecules are so strong. In this one, there is more electron than proton, so the attraction can never be as where there is balanced. And the same thing applies also as we go down the group. Even though it might be losing shell, it will still be bigger than the one above it. Let's talk about the ionization energy. The ionization energy refers to the amount of energy required to displace a particular electron, that is to ionize the atom. So as we look at it, to ionize an atom, it means it will either lose or it will gain. Now, for this guy to lose, he is willing to lose. He wants to give it away. So, losing should not be a problem for him. But for the next guy, he has 2 to lose. So, it will be more work. He has to work on losing the first one and then work on losing the second one. So, the ionization energy actually increases along the period. And as it increases along the period, it decreases down the group. Why does it decrease down the group? Because it is now getting farther and farther away from the core, from the point of attraction. So as it is getting farther and farther away from the point of attraction, it gets easier for it to ionize. So when we talk about electron affinity, we're talking about the love for electrons, the love to magnetize electrons, attract them. You see, electron affinity, actually, you find out that it decreases across the period. The love for electrons just gradually dies. The love to let go, it just dies. Because this guy just wants to give it away at all costs. And this guy is willing to give, yeah, let's give. But by the time we get to this guy, he's not willing to give. He just wants to keep his own electrons for himself. If you are willing to give me, not be, I'll collect. But he's not willing to give away his own electrons. So electron affinity talks about the tendency of an electron of a particular element to want to keep its own electrons to himself. Now that decreases across the period. So electron affinity decreases across the period and it increases down the group. When we talk about electronegativity simply talks about the willingness to collect electrons. The willingness to collect electrons. You know, the guys who are stingy and the guys who are greedy and politicians. Don't mind me, I said that. You can scrap that. The guys who are greedy and the guys who are stingy, they want to have everything for themselves. Yes, that's what we'll talk about them here. You discover that the more you go towards the other side until you get to the 7th period, you discover that they have so much greed for electrons, but the group 0, they are uninterested, they don't care. But then as you go down the group, you discover that love for electrons simply diminishes, and that's the reason why we find fluorine as the most reactive and the most electronegative element in the world, because it is so passionate, so greedy. It wants to merge, it wants to consume every single opportunity, every single thing it sees. It even reacts with gold to show you how high its electronegativity is. So this is what we have to talk about when it comes to the periodic table and properties of elements, the atomic properties. So in this particular lesson, we looked at the atomic structure, the part 2 of atomic structure, and also the part 2 of the periodic table. We talked about the atomic structures and the different components of the atomic structure, that is the proton, the neutron, the electron, how they are discovered, who discovered them, when they were discovered. We also looked at the atomic spectra. We talked about the energy losses. We talked about the different levels in the shells, the shell level and the subshell levels. We also looked at the periodic table, and we talked about the relationship between the periodic table as things move across the table and down the group. Alright, in a few seconds some questions will be displayed on your screen to test your understanding of what has been taught in this lesson. Please do well by attempting them. And if there is any part of the question which proves to be difficult, you can go over the video one more time for better clarifications. Thank you.